So hi, today I'm going to do a talk about solving Connect 4, and it's going to be a talk that kind of combines elements of both game theory and computer science. So I really hope you enjoy. So first, I'm going to talk a bit about kind of Go, which is another board game. And I'm going to kind of use this to set up the rest of my talk. Then I'll explain the rules of Connect 4, and then kind of build through step by step about how you would create what we call kind of a machine or an intelligent agent that plays this game perfectly. So what we're going to do is we're going to start with a very simple algorithm, and then we're going to progressively add more techniques and more parts to keep optimizing our algorithm until it can be used. And then finally, at the very end, I'd like to talk a bit about the future of computing. So first, this is kind of a picture of AlphaGo versus Lee Sedol, which was a game versus kind of Google DeepMind's Go artificial intelligent machine and the 18-time world champion of the game. So can someone, can you raise your hand if you've kind of heard of this game before? It was like 3 or 4 years ago, I think. Have people heard of this? Does anyone know kind of how the game ended up? You can turn your mic off and you can tell.
I think the AI one didn't hit.
Yeah, so they played, it was a 5-game series, and the AI won, I think, 4 times, all except the 4th game, which the human managed to win. And this was very, very groundbreaking, because Go is a very, very, very complex game. Just to give a kind of a quick numerical sense of how complex the game of Go is, can someone tell me or type in the chat how many legal positions you think the game of Go is? There is in the game of Go. Go is played on a 19 by 19 board, as you can see kind of in this picture on the left. And you can place stones on each of the 361 kind of intersections where the lines intersect. And someone can place either a black stone or a white stone. So how many legal positions are there? You can type your guesses in the chat and I'll see. It can be a wild guess. Okay. There's good guesses coming in. Anyone else? Okay. So it turns out that 3 to the 361 is actually a very good approximation of how many positions there are. But obviously, out of all of those positions, only some of them can actually be played because there's a lot of rules in Go. So the number of legal positions is approximately 2 times 10 to the 172 second power. And that's obviously a very big number. So then the question is Go solved? What solved means for a game is that given any position, if 2 sides play optimally, we know the end of the game. So you could give like an AI, for example, any position, and it would be able to tell you who would win, either black or white. And the answer is no, Go is not solved. And the natural second question would be, will Go ever be solved? We don't know the answer to this question, actually. Maybe, maybe not. But it probably won't be by brute force because there's so many possible games. But we already know that there's an artificial intelligence that can beat humans in this very complex game. So kind of the questions that I want to cover today are, what can computers teach us about strategy? And how can we apply these lessons to human play and use them to further our understanding of game theory, computer science, and mathematics? And I just added this. I'm sure a lot of you here play kind of computer games. And DeepMind recently released kind of a multi-agent reinforcement learning program that would be able to perform at the grandmaster level of an online game called StarCraft 2, which is obviously a very complex strategic game with basically infinite possibilities. But because these games are too complex for today's lecture, I'd like to use a much simpler example of a game called Connect 4. Connect 4 is a very simple game. Players take turns dropping yellow or red tablets into the blue grid. And then the first person to get 4 in a row, either horizontally, vertically, or diagonally, wins the game. So now I'm going to talk about how you can create a computer program that plays perfectly. How can we create a perfect computer player? So first, the computer needs to understand this position. So how can we make the computer understand a position? Well, we can kind of we can code in a position based on the moves that each of the player makes. For example, this position on the right, there's 2 ways you can get to this position. First, the red player could put a red circle in the 4th column, and then the yellow player could put a yellow circle also in the 4th column. Then the red player could play in the 5th column, and then the yellow player could play in the 5th column as well. And this would create this kind of red and yellow rectangle. So the position on the left can be described in one way as 4-4-5-5. On the other hand, it can also be described as 5-5-4-4. Obviously, the red player could first put it in the 5th column, and then the yellow player in the 5th column as well. And then repeat for the 4th column too. So there's these 2 ways that you can describe this position. I'd also like to note that you can't have more than 6 of each number in a position. Because there's only 6 rows, it's only 6 rows high. If there's more than 6 of each number, then you wouldn't be able to play in that column anymore. So I'd also like to mention that I'm following this tutorial here from blog.gamesolver.org solving Connect 4. But the tutorial is written in a coding language called C++. And I'm sure that many of you are familiar with C++, but I know a lot of you aren't. So I'm going to try and provide kind of a bit more of a simpler view of how you would go about making a Connect 4 robot. So the next question is, how can we score a position? From the perspective of a computer, we want to win the game as quickly as possible. So if we score a draw as a 0 and a winning position, if we know that the computer is going to win, then we would assign it positive points. And then if we know that the computer is going to lose, we would assign it negative points. And kind of because we want to win as quickly as possible, if our player wins on the last move, we'll assign that position 1 point. If it's the second last move, it will be worth 2 points. And then kind of going on. If it was the third last move, then it'd be worth 3 points, so on and so forth. So this isn't that important. It's just kind of a way that we make sure that the computer understands that we want to win this game as quickly as possible. So now I'm going to move on to kind of how a computer computes these positions in a simple algorithm called the min-max algorithm. So suppose our computer is kind of the red player here, and then it can either choose between a position that would lead to +5 or a position that would lead to -7. So could everyone in the chat write which it would choose? Remember that positive is good. So it's a very simple question. Okay, good. So, okay, this is good. Thank you. +5 is the correct answer. But how about in this more complex position? What would the red player end up choosing? So this is kind of a bit more complex, right? So I'm going to go through this step by step. So let's look at the very bottom level. From left to right, we know that in this very left part of the graph here, we know that between +5 and -7, the computer is going to choose +5, right? And then similarly here, it's going to choose the bigger number, which is +3. Then here it's going to be -1. And then here it's going to be +3. So this is pretty simple. It's the exact same as what we did before. So we can write the computer's choices in here as this. But remember that the yellow player is the player that's on the opposite side of red. So obviously it wants to choose the smaller number because a win for red means that it's a loss for yellow. So in this case, what would the yellow player on the left-hand side choose between +5 and +3? Could you put that in the chat? Okay, +3. And then the one on the right would also choose a smaller number. So that would be -1. And then finally, the very top red player wants to choose the better of the two options for him, which is going to be +3. So this is what we call the min-max algorithm. It's our max-min algorithm. That's because, like, as you go between the two players, the first player chooses the maximum for themselves, and then the second player chooses kind of what they perceive to be a win, which would be the minimum. So it alternates between max, min, as you can see on the right hand side of this decision tree. And that's kind of the foundational basis of what we're going to do here. So how can we code this up? In code, we're going to create an object, which is just kind of a thing, I guess, that has a lot of different attributes and a lot of different functions that it can perform. So we create an object called position. First, position will indicate whether a column can be played. Basically, what that does is it checks that at any point in time, there's less than 6 kind of tablets in that column. Then it can play a certain position, i.e., it'll drop a circle into a column of the user's choice. It can also check whether a certain move is winning or not. So what that means is it would check if kind of this position will lead to a win. For example, plus like a very good move might be +15 or something, and a very bad move would be like -10. So the computer can, or this object can check whether a move is winning or not, and it can also count up the number of moves to this point. So these are kind of the 4 things that we want our object to do. So this is kind of the code for this position object. It's in C++. This is the constructor. And so I don't expect any of you to kind of understand this or even want to understand it, but I just added it in so you would kind of know what it would look like on a computer. So then we also want to code the min-max algorithm that we saw earlier. So first, it will check if the game is a draw. So that only happens if 42 moves have been played, right? It also checks whether a player can win in the next move, and it returns the corresponding score of the position. So, for example, it would kind of check kind of all the possible next moves, like I'm drawing at the bottom, and then it would check kind of the scores of each of these positions. And then it does this recursively. And I think most of you know what recursion means. It means that kind of you would repeat this algorithm. Once you run it here, you would run it here as well, and then it would check all of its child positions and so on and so forth until you've mapped out kind of the entire game. Okay. So that's the code. So is this good enough? Well, I earlier mentioned that kind of Connect 4 was a very simple game, but there's still quite a lot of positions that we need to calculate. So here's a quick quiz. How many Connect 4 positions do you think exist? You can answer 1, 2, 3, 4, or 5, kind of in the answer choice. Give me a guess. So everyone can guess. Okay, so this is interesting. Actually, I'm getting a lot of private messages, and people think it's 1, people think it's 2, people think it's 3, people think it's 4, people think it's 5. The correct answer is actually 4. So there's over 4 trillion positions in Connect 4. So that's quite a lot, actually. 4 trillion positions is a lot of different possible games, which means that our current algorithm is nowhere near as efficient as it needs to be. If we ran it alone, our computer wouldn't even be able to play a single move because it would be too busy kind of testing everything out. So the rest of my talk is going to be on how we can improve this algorithm to make sure that we can use it. So first, the technique I'm going to introduce is called alpha-beta pruning. So the question that kind of sparked alpha-beta pruning was, what do we really need to check all of the possibilities? Well, obviously the answer is no. Suppose that you already know that a move has at least value 9. So you've already checked that there exists a position kind of in the future that has value 9. If we can verify that the other move that we're testing has a value that's less than 9, then we don't even need to explore the rest of this position because we already know that it's going to be worse. So kind of, if we know that all we really need to know about kind of these moves is whether it's better or worse than the one that we already have. And if it's worse, then there's no need to check it. So that's kind of the how alpha beta pruning came to be. So alpha beta pruning relies on a scoring window between alpha and beta. Alpha is kind of the worst score for player 1. So this doesn't mean worst, it means kind of worst verifiable score. So kind of the minimum score that player 1 can play, and beta is the minimum score for player 2. And obviously these are going to be opposites, right? So initially alpha is negative infinity, beta is positive infinity, and then you kind of do this iterative process. If the score of a position is between alpha and beta, which it obviously will be the first time because it's between negative infinity and positive infinity, then we fully calculate this position and then we update alpha to become this new minimum. So kind of a visual would be, originally the window would be, for example, like this big. And then once you find a better move for player 1, then you can kind of progressively move the arrow and make the interval smaller. Similarly, once we move to the next player, we do the same process again, and then basically we keep shrinking and shrinking and shrinking this range to restrict the number of possibilities that we actually need to calculate. I think that kind of whenever I'm explaining these kind of processes, it's very difficult to explain it based on kind of the process itself. So I'm going to do a quick example to make sure that everyone gets it. Okay, so here we have kind of a very similar decision tree to the one that we showed earlier. So if we start checking from the very left, then we know that at this point, the value of the position is going to be +3 because player 1 is going to choose, the red player is going to choose +3. But then if we go 1 to the left, we can see that the first node here is +5. So we already know that the value of this is going to be greater than +3, right? Because we already have a +5 here. So then this actually means that we don't even need to check this node, because from the perspective of the yellow player here, they're not going to want to choose this position anymore, because they know that it's worse for them than this one. So we only checked 3 out of the 4 nodes, and we already know that the value of this is going to be +3, like that. Okay, and then we can repeat with the right side of the graph. So evaluating these two positions, we know that the value of this one is -1. And what's interesting about this part is that we don't even need to check this entire tree at all, because we know that this means that the value of this circle is going to be less than -1, because we already have -1 here. So if this is better, then it would be less than -1. For example, if it was -5. But if it was worse, if it was like, for example, +2, then yellow would still choose this side of the decision tree. So we already know that this is less than or equal to -1. Obviously, because this is worse than this side, we know that red is going to choose +3. So originally we'd have to search through all 8 of these bottom nodes, but using alpha beta pruning, we've restricted that to I think 5 that we needed to check. And although this doesn't seem like a very big kind of speed up, as the trees become 2 to the kind of 20th power big, then it becomes very, very significant, especially because you end up kind of cutting out half, or like 80%, 90%, 95% of the nodes that you need to check, which makes the process a lot faster. And kind of the final position that we get is +3 for red. So alpha beta pruning is very useful in and of itself, but we also want to kind of optimize how we explore these moves. So which moves are typically better? When doing alpha beta pruning, we want to restrict the alpha beta interval as fast as possible. Basically, kind of how you want to think about this is, if you slowly choose better and better kind of nodes, then the alpha beta pruning process isn't going to help as much, because you're not going to be able to kind of make it small to the point where you can kind of start cutting off unnecessary plans. So what we want to do is we want to start choosing from the best moves. That way, we know that kind of if you choose the best move, then you're going to be able to restrict this interval very fast, which means you're going to be able to cut out a lot of the excess and unnecessary parts. So kind of, if any of you have played Connect 4, I'm sure you know this, or tic-tac-toe even, like 5x5 tic-tac-toe, moves in the center of the board tend to be very good. The reason for this is, if you're in the center of the board, then there's lots and lots of different ways that you can get a 4-in-a-row connection. But for example, if you're in the corner of the board, then there's not that many ways. So kind of a heuristic that we use is that we want to explore the moves in the center of the board first. Kind of a way that we would be able to code this would be, for every single kind of circle that you saw in the 6x7 grid earlier, you would write in kind of the number of possible connect 4s you could draw through it. For example, if you use the tic-tac-toe example, there's only 2 possible kind of wins in the corner, right? It could be either vertical or it could be horizontal. Whereas there's 3 on each of these edges. and then there's 4 in the middle, right? Wait, is there 3 on the edges? No, there's actually only 2 on the edges, I think. So in this case, you would start checking with the middle square, and then you would check the ones on the corner after. Oh yeah, it's 3 for the corner, sorry. Thanks for check. It's 3 for the corners because there's 2 horizontal ones, and there's also the diagonal. So in this case, you would check the middle first, because it's probably going to be the best. And then you would check the corners after that, and then you would check the edges. So by doing this, you can kind of optimize the order in which you're checking the moves, which is a very good thing. We also want to check which moves are likely to lose, right? It's kind of the opposite. So we don't even need to check the losing moves. If there's a very simple losing position, like for example, there's already 3 in a row in a certain column, then we know that the algorithm must block this win. So then you don't even need to check the other positions. You just need to focus on blocking the other player's win. For example, if a player has a potentially winning position, for example, if there's like, if they have 3 blue circles here, then the computer doesn't want to drop, the computer doesn't want to drop a white circle here, because then the other player could drop a blue circle here and then they would win. So there's kind of a couple of heuristics that the computer uses to make sure that they don't kind of automatically lose the game. And these moves take priority over all other moves. So up to this point is kind of how you make sure that the computer doesn't kind of automatically lose very quickly. And kind of the final thing I want to talk about is a transposition table. So I'm sure this is a very kind of new concept, but it comes from the basic idea that we want to avoid repetition in the positions that we check. As we saw earlier, 4, 4, 5, 5, and 5, 5, 4, 4 make exactly the same position, right? And you can imagine that as you keep playing this game, there's going to be like many different ways to get to the same position. And it would be a very big waste to check the position's value every time you encountered it. So we want to save or cache some of the values of the positions so that we can save this computation time. A way that you do this is called a linked hash map with fixed storage size. So we keep the most recent positions. FIFO means first in, first out. So if a position comes up, then we'll put it into the linked hash map, and then we'll eject the position that hasn't come up in a long time. And the reason that we do this is because recent positions are much more likely to come up again and again and again. So that really helps to keep these positions. And kind of this is how a linked hash map works. Basically, a regular hash map, you have a key like K, and then once you input that into the hash map, it'll return a value for you, V. So it's basically a collection of kind of KV pairs. What a linked hash map does is it also preserves the order in which you insert things into the hash map. So it's kind of a combination between an array and a hash map. So this means that you can kind of, once you add kind of the 100th position, for example, you can eject kind of the first one. And then once you add the 101st position, you can eject the second one, et cetera, to make sure that you have 100 positions at all times. So that's kind of a very basic overview of how you would code up a Connect 4 computer program. So I want you to try and experiment with kind of a version of this that was created, I think, by a couple of American programmers. So I'll give you 5 or 10 minutes to play with this link that I posted on the PowerPoint. So you can access this with your computer, connect4.gamesolver.org, and try experimenting with this implementation of the algorithm. Oh yeah, thank you. Thank you for putting it in the chat. So try experimenting with this implementation of the algorithm and try and see what patterns you notice in the opening. So I'll give you guys 10 minutes to do that. Or actually, no, 5 minutes. Play like 1 or 2 games and then come back to the meeting. Was everyone able to play at least 1 game of Connect 4? Okay. If you were able to play 1 game, could you come back to the call? So kind of what patterns did you notice in the opening? You can speak up, or you can, or yeah, I'd prefer that you speak up. Okay. So someone said that in the opening that a lot of the recommendations were in kind of the middle column. Okay. Anyone else? Did you notice whether the first player or this, if you made the computer the first player, like they would win, or if you made it the second player, they would win? Did any of you notice something like that? Okay, first player wins, right? So is Connect 4 solved? The answer is yes, Connect 4 is solved. Basically, if the first player plays perfectly, which the computer does in this case, then the first player will always win the game. And what's very interesting about this is people didn't know this for a very long time. And the person that actually found this out, I think he was either a mathematician or computer scientist or something like that, actually used a very similar method to what we'd covered so far. And what he actually did is he broke the game down into several patterns, and then he analyzed each of the patterns to prove that the first player would always win. So who knows, maybe in the future there might be kind of a discovery that the game of chess actually white always wins, which I seriously doubt. I think chess is probably a draw, given perfect play by both sides, but we still don't know because we've never kind of explored the game of chess to that depth. So finally, after I've talked a bit about kind of Connect 4, I want to talk about the future of computing. So Go is widely considered one of the most difficult and complex board games ever created. But AlphaGo is considered to have ended an era of competition between AI and humans regarding board games because it so convincingly beat kind of the best humans in the world. Sorry. AlphaGo proved that computers were capable of complex and original strategic thinking. And it also proved that kind of the methods that it used to analyze the game of Go were very applicable across a wide variety of different fields. So what's next? I'm sure many of you have heard of this concept called artificial general intelligence, but AGI is kind of, quote, the hypothetical ability for an intelligent agent to understand or learn any intellectual task that a human being can. There's a couple of different ways that you can evaluate whether artificial general intelligence has been reached. The most famous of which is the Turing test. But there's also a couple of interesting ones. For example, I think there's one that relates to college. Like, would an AI be able to attend university, learn the material, pass classes at the same level as a human? There's another one called, I think, the coffee test. Could, given kind of an artificial intelligence inside of a house, would the AI be able to go in and make themselves a cup of coffee, kind of things like that. So AGI is basically, or it's also referred to as strong AI, but it's basically the hypothetical ideal for an intelligent agent to reach the level of an autonomous human being. People thought that we would maybe never reach this point. And even the most optimistic people thought that it would be maybe 20, 30 years in the future. But AlphaGo showed that we are very, very, very close. Well, close as in not like 2 or 3 years in the future, but closer than we used to think to this artificial general intelligence. So I want to end with a quote. The fact that you all came to today's open research forum means that you're probably very passionate about either mathematics or computer science or some of the sciences. And I think that's a really great thing, and I'm really glad that you took the time to listen to my talk today. In kind of the coming years, as we grow up and we become adults and we start working, we're going to be exposed to a lot of very important technologies like artificial intelligence or quantum computing and things like, or genetic editing and things like that. So I think it's very important to realize that the ethics of kind of the technology that we will work on in the future is also very important. Here's a quote by Freeman Dyson, who was a very, very famous physicist, mathematician, etc. But he said that technology must be guided and driven by ethics if it is to do more than provide new toys for the rich. If we want to create a technology that will help everyone in the world and make the world a more sustainable and better place, then we need to consider kind of the moral consequences of the work that we do. And I hope that all of you kind of, or myself as well, but we all grow up to become kind of responsible, socially responsible scientists that take into account these complex factors when working on our new breakthrough inventions. So thank you for listening to my talk today. I hope you learned something. And yeah, I hope you continue to pursue kind of whatever you're interested in right now and do great things. Thank you.